Hello students, this video is about the discovery of neutrons. So basically in this we are going to discuss the experiment that was done by Chadwick in 1932 and from which the discovery of neutron take place. So discovery of neutron was done by James Chadwick in 1932. He was also awarded Nobel Prize for this discovery in physics. And to discover neutrons, Chadwick performed an experiment in which alpha particles from a radioactive polonium source were used to bombard beryllium nuclei. So we bombard alpha particles from polonium source to beryllium nuclei, and highly penetrating rays were found to come out of the beryllium metal. These could not be deflected by electric and magnetic fields. These radiations were then used to bombard hydrocarbons like paraffin wax. So high energy protons were knocked out from the paraffin wax when during this bombardment or as a result of this bombardment, and the energy of ejected protons was found to be too high to be accounted for gamma ray photons. So if we bombard this paraffin slab by photons, then it was not possible to get that much energetic proton that was actually they were getting in experiment. So it was concluded that by using the law of conservation of energy and momentum, that penetrating radiations consist of some neutral particles having a mass nearly that of a proton, and these particles then later on called as neutrons. So we are going to discuss this experiment only. Here is the diagram set up for the experiment, in which Chadwick used a polonium source for getting alpha particles. So they are using alpha particles which are emitting from a radioactive polonium source. These alpha particles were bombarded on beryllium nuclei. So here are the beryllium nuclei. Alpha particles are incident on these beryllium nuclei. Then highly penetrating rays were found to come. These rays were found to come, but at that time it was not known that these were of nucleus, so they considered it as electromagnetic radiations or normal gamma ray photons. But when it incident paraffin slab, the output we get are highly energetic proton, and it was not possible for gamma ray photon to give such energetic protons. That's why by applying the law of conservation of energy, it was concluded that the rays that were incidenting on paraffin slab were not gamma ray photon. These are of some neutral particles having a mass approximately equal to the proton. So that's why they call these neutral particles as neutrons. So step 1, alpha particle from polonium source is bombarded on beryllium nuclei. The rays that are coming from the beryllium nuclei, that are the highly penetrating rays, coming out of beryllium which were not deflected by either magnetic or electric field. This shows that these rays are neutral, deflected by magnetic or electric fields. Then these radiations, when knock paraffin slab The output was highly energetic protons. So before performing this step 3, till this point it was considered that these radiations we are getting from beryllium metal are gamma rays or gamma photons. But after performing the third steps, when we get highly energetic protons, it was concluded that energy of gamma ray photons is not sufficient to give such highly energetic protons. So that's why, by considering energy and momentum conservation, it was concluded that these rays are of neutral particles called neutrons, and these are approximately as heavier as protons. That's why they are imparting them a high energy. So mass of these particles is also approximately equal to the mass of proton. The reaction for the experiment, chemical reaction for it, can be written as 2He4, like we have alpha particles, so it is of helium, plus beryllium 4b9. It gives us neutron, that is 0 and 1, plus 6C12. This is the reaction for the experiment. So here 0 and 1 denotes the neutron, which have 0 charge and mass nearly same as that of the proton. Now we know that there is some neutral particle, we call it as neutron. So let's see about the properties of neutrons. So the very first property of neutron is it is an elementary particle. Neutron is an elementary particle and it is present in every nuclei except that of hydrogen. Since hydrogen is 1H1, so neutron is not present in the nucleus of hydrogen. So it is an elementary particle present in all nuclei except that of hydrogen, right? Now the second property of neutron is neutron has no charge. These are neutral and their mass of neutron is approximately equal to the proton. However, it is slightly less, so we can call it approximately equal or slightly more than that of a proton, and it is equal to 1.00866 AMU, or in kgs it is 1.6749 into 10 to the power minus 27 kg. So this is the mass of neutron. It is approximately equal to that of proton. The third property that neutron has is it is a neutron inside a nucleus is stable, but outside a nucleus it is unstable. Means a free neutron spontaneously decay into a proton, electron and another elementary particle called antineutrino. So a neutron is stable inside nucleus and unstable outside nucleus. Since it is unstable outside nucleus, so it decay into a proton, electron and antineutrino, means 0 and 1. This neutron decays into a proton, right? 1H1, that means it decays into a proton plus an electron and antineutrino and give us some energy also. So this is the reaction. This neutron decays into the following elements outside the nucleus. The next property that neutron possesses is, since it is neutral, so it don't interact with electrons. That means neutrons have low ionizing powers. Since these particles are neutral, so they don't interact with electron, that's why they have low ionizing power. Next thing is, since these are neutral, so they are not repelled or attracted by the nucleus and the electrons of an atom, so they can easily penetrate heavy nuclei and induce a nuclear reaction. The reason is because they are neutral, so they don't show any kind of attraction or repulsion with nucleus, positively charged nucleus or negatively charged electron. That's why they can easily penetrate heavy nuclei and induce nuclear reaction. These neutral particles, neutrons, are also responsible to induce radioactivity in many elements. So they are the reason to induce radioactivity in many elements. In heavier nuclei, the number of neutron is more than the number of proton. So protons, being positively charged, repel each other, and in order to maintain stability of the nucleus, more neutrons become necessary for heavier nuclei, right? So next thing is, if you have a heavy nuclei for a heavy nucleus, since the number of proton is more, so to maintain balance between repulsion and attractive nuclear forces, we need more number of neutrons to maintain the stability of that nucleus. So in case of heavy nucleus, number of neutrons is more than the number of protons. The reason is to maintain the stability, because to bind together a nucleus, we need that much nuclear force which can overcome the electrostatic repulsion force between protons and protons present in the nucleus. That's why in case of heavy nucleus we need more number of neutrons. So these are the properties of these neutral particles, neutrons, and it was discovered by Chadwick by the experiment done by using a source of polonium. So that's all for the video. For further videos, stay tuned and keep studying. Thank you.